Okay, there are a couple of things we need to focus on. Discrete mathematics, but the component is combinatorics. Right, so there are a couple of things I want us to discuss that remain very important. They actually obviously fall in succession to the things we discussed. It's very important to be in a position to determine if two graphs are isomorphic. In our previous discussion, we had graphs that actually are isomorphic, but obviously we actually saw graphs that were not isomorphic at some point. Now we're looking at these graphs here, determining with reasons whether the following graphs are isomorphic. Right, so are they isomorphic, these two graphs, or not? So we actually discussed that. So we, just by looking at the two graphs, are able to see that, look at them very carefully, and you see the fact that the examiner here in the graph that is induced by, or actually formed and spanned by one vertex 1594. It looks as if the examiner wanted to draw a graph like this, but it was just missing an edge. So, and we can see the same on the other side. And now this graph here, that is drawn on four vertices, with all edges possible between the vertices. Because if you put four vertices like this and you join them, this graph here is a special type of graph. Now, it is actually not a graph that is available here. A graph like this, we call it a subgraph because it actually is the subset of a graph. So this subgraph here is not available there. That observation makes the two graphs not isomorphic, and hence we answer the question. Right, so we note therefore that the two graphs, right, the two graphs are not isomorphic because of that observation that I said, but we're going to discuss that. This is how obviously we have to write the answer. In the first graph, right, the subgraph, this one here, right, exactly this subgraph here. Right, in the first graph, the subgraph induced by the vertices, okay, induced by the vertices A, B, E, and F. Right, that graph, that subgraph I've demonstrated in red is isomorphic. It's isomorphic to a K4. K4 means just a complete graph on four vertices. So if you put four vertices and you join all of them, you get that graph there. Whereas there is no such subgraph in the second graph. Okay, we do not have, this is just saying this graph that is isomorphic to the K4. It is in fact a K4, this subgraph, but there's no K4 here. So because of that, then this graph here has a subgraph that is not there, so the two cannot be isomorphic because of that. Right, so moreover, there's also some tricky reasoning that is possible, some detailed, deep analysis. Right, so alternatively, one could also observe that the first graph has 11. So it's possible to make the observation that the first graph has 11. Right, so has the first graph has 11 4 seconds. Okay, so in the first graph, there are 4 seconds. For example, the A, B, F, E, A. It's a 4 second. Now, also you can look at the A, D, I, E, A. It's also a second. And you also can look at the B, F. So they're 11 of such. Right, so the first graph is 11 4 seconds. Let's deep analysis of that. But you don't need to state which ones because it's a long list, and time is not in these assessments in the exam. Right. So while the second graph, right. So while the second graph um has only 8 4 seconds. Right. So if you count them carefully, right. Obviously, if you 4 seconds, the 5, 6, 7, 9, 5. Okay, is 1 4 second. What other 4 second is there? There's also the 2, 7, 8, 3, 2, right? And there's another 4 second, which is 4, 5, 9, 8, 4, right? So, but now there'll be there are 8 of such 4 seconds in the second graph, right? Um, and because of that, or you can say alternatively, the first graph, has exactly 8 3 seconds, while the second graph is only has only
Hello?
3 seconds. Yes, please.
How did you get 11?
Yeah, the 11 4 seconds. So obviously, if you need to identify them. So let's look at how many 4 seconds are there. Let's look at the A, E, F, B, A. These are 4 seconds. Okay, that is one. And now there's another one, A, D, I, E, A. Two, E, F, G, I, E. Three, right, F, B, C, G, F, B. Okay. You have 4, and now you have D-I-G-H-D. You have 5, and then you have G-H-D-C. You have 6, and now with this, actually, you realize that ultimately you get a total of 11 of the full circuits. Okay, you can already spend time, you can list them carefully, but they're 11 when I counted. But also, while the second graph is only 8 full circuits, okay, but obviously you need to spend time and make sure that you do them very, very carefully. But you will realize that they are full, 11 full circuits, or there are other 11 full circuits. But you spend time on this, I can always give the list of all of them um, after the lesson. Okay, after discussion, I can always list all of them down very carefully. But there are 11 of them. But most importantly, in the exam, um, you don't need to state them. You don't need to extract them quite. You need to state how many they are and how many they are in the next one, and therefore the two graphs therefore are not isomorphic. Then to give the exhaustive list because of the time constraints, the list normally becomes exhaustive. Right. So obviously we summarize the observations, but once again, I can always extract all of them and send the list. In the same way, in the second one, or alternatively, somebody can say there are 8 3 seconds. In the first graph, there are 8 3 seconds. Okay. Right. What is an example of a 3 second here? Right. A 3 second would be A, E, F, A. Another 3 second will be A, B, F, A. Right. And you count them carefully, you list them, and now you realize, therefore, that they are not the same number. Those seconds that are not, it doesn't matter what seconds, those seconds that are not the same number. In particular, it's easier to identify the 3 seconds because there are too many triangles here. There's a triangle there, there's a triangle here, there's a triangle there, there's a triangle there, there's a triangle there. So these too many triangles suggest that, okay, one can start counting the 3 seconds. But if one counts the 3 seconds, you realize the 8 in the first, while the second one is only 3 seconds. Okay, but I must indicate that one can always count them, and I can always send the list of these seconds. But yeah, there's no need quite normally to list them out in assessments because of the time constraints and the fact that the list can take a reasonable amount of time to complete. And it's not necessary to normally for the list to be seen of all the circuits, listing them, etc., and filling the whole page. Is not normally not necessary. But well, I can always send the list. Right. In the next question, we're looking at you need to list all non-isomorphic graphs with 8 vertices, where each vertex has degree 2. How many graphs are there? Okay, this is a kind of a question. You need to draw it by experiment. You need to experiment this. So if you say there are non-isomorphic graphs with 8 vertices, where each vertex is degree 2. Okay, there are so many possible drawings, but there's an isomorphism between them. So you always get that there's an isomorphism between such graphs. Okay, so but in short, there are 3 such graphs, and I shall draw them. But I mean, any graph must be isomorphic to one of the 3. There are 3 such graphs. I know somebody can see another kind of graph, in which case to be isomorphic to one of them. Right. For instance, somebody can have this graph with 8 vertices. Somebody can draw the complete graph on 3 vertices, and then they can draw this one here on a graph on 5 vertices. Not necessarily complete. Complete means all the edges have been joined, and there's no edge that's missing between edges. There's no rather yes edge that's missing between vertices. Right. So if you look very carefully at this point, this one here, right, this one here, you have this, you have that, you have this, you have that. So you have, so this one goes there, and this one goes there. This one goes there. This one goes there. This one goes there. Okay, so this graph is actually, I know the graph, the diagram is not very clear, but yeah, it's a graph on 8 vertices, right? Because there's 3, so this is one graph. You have the graph on 3 vertices and um, a graph on 5 vertices, right? So, but on 8 vertices, somebody can have a graph that this one can be broken down into a graph on 8 vertices. You can do 4, 4. You can do 4, 4. Right. So this 4 plus 4 is 8. So it's also a graph on 8 vertices. This now, but they are not isomorphic because this one has a 3-second, but there's no 3-second in this graph. This graph that's formed by the two graphs. This one has a 5-second, but this one is only what? Is only composed of 4 seconds. So these two graphs cannot be isomorphic. Now, also, you can look at one graph that is on 8 vertices, like this. So you put a vertex here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these graphs are not isomorphic. We make that comment that the graphs are non-isomorphic. The non-isomorphic since the first graph, we already discussed that. Since the first graph contains a 3-second. Okay, so we have a triangle there. So it's a 3-second in the first graph. The second graph um, the second graph contains a 4-second. So here we have 2 4-seconds, but here there's a 3-second, there's a 5-second there. So this one is a 5-second, but the others do not have 5 seconds. So in other words, these are actually non-isomorphic graphs. Right. So the second graph, for instance, contains a 4-second, and the last, right, the second graph has 2 4-seconds, and yeah, the second graph is a 4-second, right? And the last one, and the last graph, right, and the last graph contains an 8-second. The truth is, if you look at the fact that the last graph contains an 8-second, so the other two graphs do not have an 8-second. So as a consequence, then it's very clear that these 3 graphs are non-isomorphic graphs, okay, because of the differences in the seconds in each of these. Right, so obviously the last one contains an 8-second. Okay, because of the presence of seconds of different lengths, of different sizes, we infer or conclude, therefore, that these two graphs here, or these 3 graphs, are non-isomorphic. So list all non-isomorphic graphs with 8 vertices where each vertex has degree 2. Each of these vertex has degree 2. Why? Because it has two edges incident to it. You have two edges incident to each of the vertices, so you have that. So you have that. You have that. All right. You have that. Okay, we continue. Now we look at the next question. We need to determine the complements of the graphs in A. What are the complements of the graphs in A? Okay, let's look at the idea of complements. Right, we note therefore that the complements are given by right. In the first graph, we saw that we had a 3-second, and then we also had a 5-second. Okay. So in the second graph, maybe I can make something bigger here because this is too small. It's going to create an issue. It's going to make the whole thing very, very unclear. Right, because we are yet to draw the complement, etc. So we had a triangle like this. I'm going to something else now. I placed something else. Okay, right. So we have here 3 seconds, and then 5 seconds. Something like this. All right. Now let's look at the next one. Right, we had 4 seconds here. So we had a 4 second, another 4 seconds. So we had 4 seconds here. And then thirdly, we had an 8 second. Right, so it was just one here. Okay. And one there. Okay, so we have that. So at the end, the complement will be joining edges that have not been joined. So this one was a 3 second like this, and those edges were joined. But now um, in the other one, we're gonna join other edges. So these were joined, but now here we're gonna join this one and this one. Okay, here we're gonna join this and that, because this triangle was was not connected with the other one. They were not joined. Right, so we have this one. So you have this one. You have this one. Okay, so you are joining all the edges, but obviously the triangle was not joined with the graph on the 5 vertices. So you join now the graphs that the edges that were not joined. The easiest is just joining the, so we can't join these ones because they were joined. These were not joined, so we can join them. These were joined, so we can't join them. All right, we have that. But this one, uh, right, so this one, and then this one here. Right, so you have this one, we're not joined. And then this one, we're not joined. Okay, I understand this. This is not going to be very clear. Right, so I'll try to put the message across. Um, okay, this one, this one. Uh-huh. This one. This one. Okay. Okay. Let me see now. This one. All right. This is just the idea. But yeah, it's very, very dense. Okay. I'm yet to, but now let me just mention the following: that here I will have two, two, four, five, two, four, five. Uh, two, four. Here there must be five. This is of degree five, right? And then this one also is of degree five as well. Okay, because it's not going to be, it's not very clear, right? This one is of degree five as well. Okay, I know that I can be missing something here. Let's see what edge is missing. Appear to obviously have not drawn this one. Okay, you forgive me because it's not clear, but that is just the idea. So now, basically each of these has degree five. Okay, I'm just saying, therefore, you can just complete just in case I missed an edge. Right, so, but also now we come to these ones that were 2 4 seconds. You can join this one and that one because they were not joined. And then now also this, because these 4 seconds were separate, you can join these guys here, these vertices. You can also join because these were separate. So these ones, you just join any vertices that we did not have edges between them. And then now, this one here, you can join this with that. You can join this with that. Okay. And then you can join this one with this one here. Okay, you can join this one with this one here. You can join this one here. Okay. Okay, you can join this one with this one here. You can join this one with this one here. Okay, as a consequence, you see, you can join this one with this one because they were not joined. This one is this one because they were not joined. can join this one because they were not joined. You can join this one because they were not joined. This and that because they were not joined. Right. Mm-hmm. 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 Right. So these guys here, okay, these ones because it was just in 8 seconds. So these were not joined, but you can join any of these that are not joined, like this. And also join this one. Is that what? Okay, but also I need to mention that each vertex here is of degree 5. Each of these vertices. Okay, let's see this one. You just keep joining because these were not joined. These were not joined. Let's see now. Okay. Um, these were not joined. Okay. These were not joined. All right. I know it's going to take time, but yeah. Right. So that is just the idea. After joining all this, but you realize therefore that each is degree 5 also here. Okay, because you're saying determine the complements of the graphs in A. So these will actually be the complements, but yeah. Here, this one, you need to join any vertices that are not joined. Okay, this one will go here, and this one will go here.
You hear me?
Yes, please.
Uh, shouldn't there be a line here?
Um, yes, please. In particular, a line is necessary. I know that I might have missed some one or two lines. Right, I might need to check very carefully, but that's a rough idea. Right, but I know that this is not to scale, so for instance, you see, this is 2, 4. I need one edge there, so there's an edge that's going to be from here to there. Okay, I mean, these are not ready to scale. I must state that. Right, so thanks for realizing that. But yeah, each of these has degree 5. Right, okay, but obviously still actually must be drawn. There must be still some edges here. This one will come there. This one will go straight to that because there was nothing like that. This one will go straight to there, and this one will go straight into there. Yes, my dear. All right. Okay. So yeah. Um all right. All right. That's fine. Okay. Okay. That's fine. Thanks, my dear. Okay. So we continue. We continue. So if we continue. Okay, we continue and we have that. Okay, let's check again. All right. I mean, this will just be okay. The best sometimes is to draw the original graph and then just use colors. You can draw the one in red and the other one in the blue color, just to make sure that you exhaust all possible possibilities here. Because now, for example, this one goes there, but you'd need an edge that goes there like this. Okay. But in the end, now, for instance, you need an edge that goes like this. Okay, but in the end, each one will have degree 5 here. Right. So that's just the thing. I know I might be missing an edge somewhere. But degree 5, meaning that there's 1, 2, 3, 4, 5. But for each one. Okay, if I'm missing an edge, you will forgive me. Because um, it's a possibility. Here there's 1, there's 2, there's 3, there's 4. And so you need just one more edge that's going to run from top to bottom. For instance, okay, I drew it there. Okay, thanks for drawing one edge that is going to run, for instance, from here to there. So that kind of thing, right? So I know I might be missing an edge somewhere, but yeah, each one must be of degree 5. So just note that. Right. So and we need to determine the complements of the graphs in A, and these are roughly the complements. I know they're not very clear diagrams. You can use straight lines. So you need to use rulers to draw these as possible to do so. Let's look at the next question. Right. How many non-isomorphic graphs are there with 8 vertices where each vertex has degree 5? Okay. So we're looking at non-isomorphic graphs that are there with 8 vertices where each vertex has degree 5. Okay. Prove your answer. 3 marks. Okay. So here we need to prove our answer. How do we do this here? Right. To do this question, we need to answer first how many non-isomorphic graphs are there with 8 vertices where each vertex has degree 5. We saw that each vertex had degree 5 in the previous question. So these actually cuts down the amount of work. So each graph is a graph on 8 vertices, but each vertex has degree 5. Right. So now at this point, if we then say prove your answer, this is done in relation to the previous question. So because it would just be have a bit more work to analyze these normally. For one can actually consider any graph G, right? Any graph G with 8 vertices, right? Any graph G with 8 vertices, for instance. In each of degree 5. Okay, like any graph G with 8 vertices on each of degree 5, like we saw previously in the previous set of complements. Right. Probably it follows, therefore, that then its complement, G complement, still has 8 vertices. Okay, still has 8 vertices. So at this point, we note, therefore, that its complement G bar still has 8 vertices. But okay, we analyze the fact that right, but now each degree is 2. Why is each degree 2? This is the case, obviously, since we'll analyze that together right now. Since they are in total, 7 possible neighbors for a vertex. Okay, now we're looking at the complement. We're saying if a graph has 8 vertices, surely the complement will still have 8 vertices. We saw that in the previous question. But we are arguing that, but now each will have degree 2. Yes, it is true. Since they are, since they are in total, right, since they are in total 7 possible neighbors for a vertex. Okay, for instance, here's a graph, each of degree 5, and it's an 8 vertices, each one of these. Then the complement of this, each one has degree 2. So we saw that. And it can be explained, obviously. Like we have you have a graph of on eight vertices, each vertex of degree 5. And then when we get the complement of the graph, whose each of whose vertices of degree 5, the complement is of degree 2. Okay. All right. We need to mention. Okay, we make reference to this question. In A, the graphs we drew each had degree, um, each vertex at degree 2. But now the complement in the complement graphs we saw each degree was 5. Right, we make reference to that, and we say that in A we found, just state that because this refers to the question is much of an investigation. This we found all such graphs, right? So to find the graphs to find the graphs with constant degree 5. We saw those ones with constant degree 5 in the previous question. We just took the complements. So we just take the complements, take the complements again. Right, so obviously if you take a graph and take the complement of the graphs in A, you get the graphs in B. If you take the complement of the graphs in B, you go back to those in A. We take the complements again. Okay, so yeah. Most importantly, well, obviously we state here that since the complement of the complement gives the original graph. Right, so since, in other words, if you have to find the complement of the complement, then it's the same as just the graph G. Right, since the complement of the complement, right, so since the complement of the complement of G, since the complement of the complement of G is just G again. It's just G again. All right, so we see that here, the complement, double complement is just G. How do we know? We said you had these graphs, we took the complement or the complement of each, we got these graphs. So if you could take the complement of this, then we join these, we could join these and we could get back we got back to the graphs G. Okay. So this is quite an important discussion. Okay, we note therefore hence the only possible such graphs are the three graphs in B. So obviously, they ask us how many nine isomorphic graphs are there on the 8 vertices, each of degree 5, constant degree. So we can see that there are only 3 such graphs there. All right. So the answer to the question is there are three. There are three there are three such graphs. Um, there are three such graphs. Okay, continue. Okay, so this is just an exploration of the experience in the two previous questions. So it would require a lot of reasoning, but yeah, we have that. We have exactly that one there. We have exactly that one there. We continue. Okay, so the answer is there are three such graphs. Okay. Um, 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 um. The details are there in the graphs. They're very evident. So the truth is somebody would have to draw, but the drawing's already there. So the marks are 3 because you just need to write a summary of the observations. Next one. All right, so you continue. Right, so in the spirit of the previous question, right, so we continue with the notion of proofs here. Prove that if graph G, or if G is a graph with the property that each vertex has degree 6, has degree at least 6, then G is not planar. Okay, so you continue. Okay, so you continue. Right, so in the spirit of the proofs, this exam was, these are past exam questions. Um, so yeah, prove that if G is a graph with the property that each vertex has degree at least 6, then G is not planar. Um, okay, so you continue. So prove that if that, okay, we have seen the question. So we use a theorem here. We use Euler's formula. There's something we call Euler's formula for a planar graph. Okay, where we determine the number of the edges is less or equal to 3 by the number of the vertices minus 6 for a planar graph. So we're going to use this theorem to prove this. We're going to use this theorem to prove this. Okay, let's prove this one. So using this theorem just to prove the planarity that G is not planar, we begin as follows. Right, so we let the number, so we define the symbols so that V is the number of the vertices and E the number of the edges. So let the number of vertices be V and the number of edges E. Okay, we're just saying V is the number of the vertices and E is the number of the edges, and we want to prove that therefore the graph G is not going to satisfy this, because if it's planar, the number of the edges must be less or equal to 3 times the number of the vertices. All right, so we continue. Each vertex, they said here with the property that each vertex has degree at least 6. So we use that and we say each vertex has degree at least 6. Okay, at least 6 is critical to 6. So what does this mean? We observe therefore that we can add the sum of the degrees. Thus the sum of the degrees is what? Remember that this graph is the property that each vertex has degree at least 6. Right, so what is the sum of the degrees? So the sum of the degrees is at least 6V. The sum of the degrees is at least 6V because each vertex is at least that, has at least degree, has degree at least 6. So obviously we understand therefore that each vertex has degree at least 6, and therefore the sum of the degrees are at least 6V. If V is the number of the vertices, obviously we're not told how many vertices the graph has. But we're just saying V the number of the vertices in view of Euler's formula for planar graphs. But we note that the sum of this, of the degrees, equals the sum of the degrees equals twice the number of the edges. Okay, we saw that it's the first theorem of graph theory. So if you take the degrees of the sum of the degrees, where V is from the set of vertices of G, it is equals to 2 times the number of the edges. Right, we stated this one last time. And this here is the first graph, is the first theorem of graph theory. Right, so if it is the first theorem of graph theory, we know that it is the case there. So this is E. Right, it is the first theorem of graph theory. First theorem of graph theory. So the sum of the degrees, I mean, equals that. In view of the first, if you add the sum of the degrees, you get twice the number of the edges, is the theorem. Right, so and we observe therefore hence that twice the number of the edges is at least 6V. Twice the number of the edges is at least 6V. Okay, in view of this observation, the sum of the degrees is at least that. If the sum of the degrees is at least 6V, the sum of the degrees equals 2E. So it means therefore the sum of the degrees would be 2E. Which should be at least 6V. Okay, so it just this sentence here has been written like this. This equation brings about this. Okay, we can simplify that. So now at this point, you can divide by 2. Divide by 2 means the sum, the number of the edges is at least 3 times the number of the vertices. However, such a graph cannot be planar. Be planar Euler's formula, we're arguing that if the graph does this, produces this, because now if it's planar, it must be -6. But now we're getting this. For so yeah. Okay. We continue. All right. Right. Continue. However, such graph cannot be planar. Euler's formula, because there must be a -6 in view of Euler's formula. So Euler's formula right. Euler's formula gives for a planar graph we continue. We continue. Euler's formula for a planar graph Right, what is the formula for the planar graph, which says the number of the edges is also equal to 3 times the number of the vertices minus 6, which implies that right. So it would therefore imply that E is strictly less than 3V. Okay, if you drop the minus 6, because if you subtract 6, then these things are almost equal. So if you drop this one, so it means therefore the E itself is going to be much smaller. It's going to be much smaller than 3 times the number of the vertices. And that is very important. Very important. So we look at this one. But our case, right. But in our case, let's say, right. But in our case, we have E is greater or equal to 3V, according to this. And that is enough to say this graph cannot be, G is not planar. So we conclude that G is not planar, you know, and we're most certainly done. So G is not planar, and we are done. Right, and we are done. Next question. All right, so we need to determine the largest number of vertices that a connected planar graph with 10 edges can have. Give an example of a graph attaining the maximum. Right. Determine the largest number of vertices that a connected planar graph with 10 edges can have. How many vertices can this be? A connected planar graph with 10 edges can have. Give an example of a graph attaining the maximum. So we answer this question. Right, to answer this question, there are a couple of things you need to consider. Right. But first we speak about trees. There's special types of graphs. Right, so trees themselves are connected. Okay, we still need to discuss trees, but they're not a big deal in this module. Right, so trees are connected graphs with as few as possible edges. Okay, we'll discuss briefly trees. We looked at examples involving trees last time. Hello, my dear. Okay, just 1 second. Right. Okay, that's fine. All right. Right, so continue. We continue. Right, so going on. We effectively are saying trees are connected graphs with as few possible edges. Right. We need to give an example of a graph attaining the maximum. So let's discuss this. Right, trees are connected graphs with as few as possible edges. Right, now since the removal, okay, we'll discuss this in detail, of any edge. Okay, if we remove any edge, what does that do? It actually disconnects. It disconnects the tree. It disconnects the tree. The reason, obviously, I mean, you can look at a binary tree, a simple binary tree on three vertices with the roots and leaves. Okay, we're here to discuss at some point trees a bit in detail, some detail, but yeah, they're not a big deal here. Really. They'll just normally be just a question on trees. Right, so special types of graphs. But since the removal of any edge, it disconnects the tree. Okay, if you remove an edge, we remove this edge, so the tree is going to be disconnected. So this vertex is going to be on its own, for example. That's said to be disconnecting the tree. But most importantly, we note that since a tree on n vertices has, okay, this is a theorem, right? So a tree on n vertices has n minus 1 edges. Okay, like this one, it's a tree. It's a tree on 3 vertices. How many edges does it have? This means that it has 3 minus 1 edges. Okay, you just take the vertices in minus 1. So you get 2 edges. Obviously, you can count 1, 2 edges. So the trees have just one less when you count the number of the edges. When you count the number of the edges, so we continue. Right, so obviously we note that since a tree on n vertices has n minus 1 edges, the largest number of vertices that a connected, right, a connected graph with 10 edges can have is, right, we note that the largest number of the vertices that a connected graph with 10 edges. What is the largest number of the vertices? Right, then the vertices will always be one more. So if you have 10 edges, therefore the vertices will therefore be 11 of them. And have its 11 vertices. Okay, what is the meaning of all these? Okay, we note that moreover, the trees are not cyclic graphs. So, right, so since trees themselves are acyclic. They're not cyclic graphs like we saw, like the other graphs. They always have roots and leaves, etc. And the children. We'll discuss the components of trees. Right. So since trees are acyclic, they are necessarily right. So they are necessarily right. Just one sec. Right. So they're necessarily what? Okay. Um. So they're not cyclic, like the graph we saw that was on 8 vertices. It's just a cyclic graph. Right. So these trees themselves are acyclic. They are necessarily planar. Right. We'll discuss the planarity of the trees in view of Euler's theorem, the one we just saw now with the -6. They actually mostly satisfy the theorem, and hence, because you can use a theorem to test if a graph is planar. But there are other ways to test the graphs. You can use the second chord method. We'll discuss that. I'm sure there's a question that's coming on that. So they're necessarily planar, and hence the largest number of vertices that are connected in a graph with 10 vertices, but first 10 edges, according to this, you can have is 11. We make a couple of observations about this. We say for instance, a path. You can draw a path. A path on exactly 11 vertices is an example. Is an example of such a tree. So we draw 11 vertices. 3, 2, 4, 2, 4, 6, 8, 10, 11, and we just connect them. You can just draw a line and then put the dots on, just to make sure that your line is straight, pretty much, and it's neat, etc. So now with that, a path on 11 vertices is an example of such, because you're able to see that this is a path on 11 vertices, and therefore, what is the largest number of vertices that the path has, for instance, right? So obviously we've seen that it's a path on 11 vertices, and the edges themselves are always one less. Okay, so at this point you can see that the edges themselves, if you count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're counting 10 edges and you're counting 11 vertices. So obviously this one here is just a path on 11 vertices. And now this question that was saying determine the largest number of vertices that a connected planar graph with 10 edges can have. Give an example of a graph attaining the maximum. Okay, so what do we then have? So obviously what we have is that we have 10 edges and 11 vertices. Okay, so we have that. We have that. So we've given the example of such a graph, which is a path on 11 vertices. But also we determine the largest number of vertices that a connected planar graph with 10 edges can have. Right, so obviously, because of the trees being planar, they were an easier way out of this question. An easier way out of this question because trees are easy to characterize. You just look at the number of the vertices and the edges are just one less, but it does not apply to just any other general graph. Okay, we're back to our usual stuff, and this is very exciting. We're back to chromatic numbers and the coloring of graphs. So we need to color our graphs to make sure that our graphs are colorful, and therefore we color the vertices of this. Right, so obviously now coloring the vertices is standard practice. We need to make sure that this one is a given color A, B is a different color, and so on. Right, for the graph G below, for example, you need to determine, right, the chromatic number of G, give a minimal coloring, and a proof that a smaller number of colors is not possible. So we always give the chromatic number. The chromatic number, we argue that what we give a minimal coloring, and therefore a proof that that coloring is the least. And so there cannot be a smaller one because we force, otherwise we don't want too many colors. We need a minimal coloring. All right, so let's look at this question. Right, if you look at this question, what do we have here? Okay, this is the in the exam. The question like this. So yeah. Okay, we can see that if you look at vertices A, B, C, E, A, B, C, E. This one is actually a complete graph on 4 vertices, because if you have those 4 vertices, you can't, it's complete because you can't, there are no other edges that are missing in this graph here. So there's no way, there's an edge there, there's an edge there, so it's a complete graph on 4 vertices. Right, so, but now this, since, right, let's see, and right here, since the subgraph induced by the vertices A, B, C, and E is isomorphic to a K4. Complete graph on 4 vertices, this one here. And there are several such graphs in this one. Right, it follows therefore that the chromatic number of G, because a triangle is a complete graph on 3 vertices and means the colors are less than 3. So, but here it will mean the colors are at least 4. The chromatic number is at least 4. So you need the minimum of 4 colors to color this graph. Now, next, okay, next, we attempt a paused for coloring of the vertices of the graph. We attempt a forced. So next we actually attempt a forced for coloring of the vertices of the graph. What do we do here? Color vertex A with 1. Okay, if we color vertex A with 1, B with 2, C with 3, and E with 4. So B with 2, C with 3, and E with 4. Suppose we do that because we need 4 colors because of the K4. K3 means 3 colors. So those are the things there. Okay, then D is adjacent to colors 1, 2, and 4, and has, okay, we'll discuss this, and it's to be colored 3, to be colored. Okay, let's look at vertex D, for instance. Here is D. Right, we're saying it is adjacent colors 1 and 2. These adjacent colors, for instance, these adjacent colors 1, 2, and 4. Here is D, the adjacent color 1, the adjacent 2 is adjacent 4. And has to be colored 3, so it can only be 3, this one. Okay. Right. Similarly, F is adjacent F which is adjacent. It's adjacent to colors 1, 3, and 4. Okay, let's look at F. It's adjacent 1, 3, and 4. And it's to be colored, must be given a color different from the adjacent ones. And has to be colored color 2. So F now must be color 2. Now G, okay, let's look at this one. Okay, now G and H, okay, let's look at the vertices G and H. So we have G, H, and I that are left. So we can focus on G and H for the start. So now G and H, G is adjacent to what? 2, 3, 4. What about H? H is adjacent 4, 3, 2. Okay, even this one 4, 3, 2. So now G and H, you can put them together because they're adjacent pretty much same colors just to avoid the writing an essay here. So now G and H are adjacent to colors 2, 3, and 4. And has to be colored 1. Okay, we have 4 colors. So there's 3, there's 2, there's 4. So G can be colored by color 1, but also H also because it's 3 here, 2, 4, and it can only be color 1. So now we have a dilemma here. Because now you can't have color 1 adjacent color 1. But since G and H are adjacent, we can see that these two are adjacent, and now it's not possible to have this kind of coloring because now you can't have two adjacent vertices having the same color because the idea of coloring is to have adjacent vertices with different colors. But since G and H are adjacent, they have to be colored differently. Hence, 4 colors are not enough. And so chi of G. So it means the chromatic number, chi of G, must be at least 5. So we need 5. The 4 are not enough because they lead to problems here. Um, The following is a 5 coloring. The following is a 5 coloring, so we just need 5 colors. It's a 5 coloring. The following is a 5 coloring of the vertices of the graph. Right. So how would a 5 coloring look like? So you'd have this table here, and then you have color 1, 2, 3, 4, 5. So color 1 is AG. Okay, we saw that A and G would have color 1. Color 2 would be for B, F, and I. For B, write F, and I will also be 2, because if this one, then this one is going to be 5, for example. So color 3 is for C, and also color 3 is for D. Color 4 is for E. Color 4 is colored, it's for E. But color 5 now is for H. H is for color 5. What is the conclusion? So this proves that the chromatic number of G is actually less or equal to 5. And so the chromatic number is greater or equal to 4, but is less or equal to 5. The conclusion from these two inequalities is that the chromatic number is 5. Okay. So we have answered this question. But we have also, so we have the chromatic number of G, and we have given a minimal coloring, which is, we notice therefore that first and foremost, because this one is isomorphic to K4, the coloring is at least 4. Okay, so in other words, you have 4 is the minimum. And now you have to give a minimal coloring. When you do that, and you prove that a smaller number of colors is not possible. And obviously, we have proven that you cannot have a smaller number of colors than 4, and the number of colors is actually 5 there. Okay, we continue. Next question. Right, in the B part, we look at the most interesting of things, the second chord method. Right, so for the graph G below, we have seen this graph, and there will always be a graph in the exam. You have to determine whether G is planar. Determine whether G is planar. Now, so you have to give full details of this. Whether G is planar, give full details of your reasoning. If it is, give a planar drawing. Okay, we shall look at that. If it is planar, you give a planar drawing. If it is not, give a subgraph, which is a K33 or a K5 configuration. Okay, We discussed configurations, but we'll discuss them just now. Okay, let's look at this question here. Right, first things first. We consider the Hamilton second. So we consider the following Hamilton second. We consider the following Hamilton second. Let's look at one Hamilton second. So we start from A, and then we go to F. Okay, this is through reasoning and trial and error. You need to look very carefully. So if you, because you don't need to repeat the edges here. Right, so you move from A to F, then you go to C. It's not the only one that can have a path through all the vertices. Then you go to E. After E, you go to H. After H, you go to I. After I, you go to G. After G, you go to B. After B, you go to D. After D, you go back to A. Right, so if you look at these here, no vertex has been missed here. Okay, this is just one, but you can find many other Hamilton seconds. So you consider the following Hamilton second, which is AF, C, E, H, I, G, B, D, A. Okay. So you have A, F, C, E, H, I, G, B, D, then A. So now by inside outside symmetry, by inside outside symmetry, we choose the edge BC to be drawn inside. Okay, we shall look at these together. Okay, like we need to choose where to draw the edge, either inside or outside in view of the Hamilton circuit we have. So at this point, we can choose to draw the edge either inside or outside. So if you look at B, and C. So we choose to draw this one inside. You can draw it, we could draw it outside like this, but yeah, there's no reason to go out yet because it's the first edge. So by and large, the first um, edge, which is called a chord. So we draw the first chord inside. Now there is another edge. Then the edge AE has to be drawn outside. Okay, if we look now at A and E, we must draw that one outside. Because if you draw it inside, it's going to cross. So we must draw it outside. So we started by looking at the edge BC. And we drew it inside. Then we looked at the edge AE because you can see it was going to cross here. So we drew it outside. But also it crosses even in the K4 diagram. So, right, so we just make that observation. Okay, in the second chord method, which we're using here, the second and the chord, we just avoid crossing edges. Then the edge AE has to be drawn outside. Now, the edge FH cannot be drawn okay, let's look at FH. Right, so if you look at the edge FH, here is F and here is H. The edge FH cannot be drawn inside. Okay, I'll put two words drawn here. Cannot be drawn. Right, so if you look at FH, cannot be drawn inside or outside. Inside or outside. Hence the graph is not planar. FH. So if you look at edge FH, you make it dash like this. We're forcing it. It's already crossing. But can we go like this? No, it's gonna cross. The other one. Can we go like this? It's also gonna cross. So there's just no other way. And this means the graph is not, hence the graph is not planar. The following is a K33 configuration. Right, so the following is a K33 configuration of the graph. So you have this one here. You have this one here. And 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 you have this here. Okay, so we draw first the K33. So this is how we draw a K33. So the A must go to F, but the A must also go to B. And then now this one must go to F, but it must also go to E. K33. Okay, let's see. This one goes there, it goes there. This one goes there, goes there. Okay. Okay, at this point, each one must have degree 3. That's a check. Okay, this is not to scale, yeah, but each degree is 3 here. Okay, you can just draw this one properly. And I just draw this one better. All right, pick my pen here. Okay, so you can just draw this one like this. Making degree 3 for each one. Okay. But now, after these, then let's draw the K33 configuration. We look, for instance, at edge AB, AB. If you look at edge AB, right, edge AB, according to this Hamilton circuit, D is there on AB. So in other words, you can put D here. Okay, let's look at also HB. Right, so if you look at HB, for instance, here is H and here is B. Right, so if you look at H and B, you have I and G in the middle. So you can put I here. And then you can put G here, like this. So this one is the K33 configuration that has been drawn. But obviously we can see that this K33 uses also the Hamilton circuit we discussed there. And so, but obviously here we have to determine whether G is planar. And said the graph is not planar. Give full details of your reasoning. If it is, give a planar drawing. If it is not, give a subgraph, which is a K33 or a K5 configuration. We've given a K33 configuration. Okay, so we have that. Okay, we're here to discuss configurations a bit more. It's necessary we do so. Next question. Right, so at this point now we are really saying for the graph G below, determine whether the complement of G has a Hamilton path. Whether the complement of G has a Hamilton path. what is the complement of G? So first we note that the complement of G at this point, the complement of G is given by, okay, what is the complement of G? If this is the graph G, what is the complement? So we saw how to draw the complements. We just we connect edges, vertices. We connect vertices that were not connected before. Right, so we're gonna have this one, and then we have this one, this one, you have this one, you have this one. So let's look at the complements now. Okay, we'll just proceed to just connect edges that are not connected, like this one. Okay, let me call this one A, B, C, D, E, F, G, H, I. Can I use a different color, perhaps? Right, so now let's connect A with G, right, and then A with H, and then D with H, let me see, A with I, and then D with C, and then this one with this one, and then this one is this one, and then this one is this one, G and F, EI, IB, okay, and then D goes with H, DF, okay, let me see, AI, okay, continue, okay, continue, so we continue, so we have this, we have this, okay, I'm just looking, please, B and F, okay, so this one is degree 3B, and also this one, A is degree 3, C must also be degree 3, so we But we can see that C and G are connected, but also C and I are not connected. My apologies that these lines are not straight. Find a better way to draw this. Use a better program to do this here. Okay, let's see now. So we have this. So here there are three, degree 3, degree 4, degree 4, 2, this one, degree 6, 2, 4, 6, degree 3, degree 3, H, okay, and then E is there. They are, all right, degree 3. Okay, it looks like pretty much what is required here. Okay, it looks like pretty much is required. Okay, we're looking at the complement of G. Okay, let's move on. Now, this is the complement of G or redrawn. You can draw it again differently. You can draw it again differently. Right, or redrawn. Ah, all right, the word redrawn must be clear. Yeah. Right, so or redrawn. Right, so redrawn. Right, or redrawn, we have the following. So we have this. Okay, let me use red. Otherwise, this whole thing is just a bit unclear. Right, so we have vertex A here. You can redraw it like this. You can put G here. You can put H here. You put D here. We put F here. We put B here. We put C here. We put I there. And then we put E here. Okay, we draw some chords here with some edges. So we draw, for instance, GC, right? BH, FD, GC we've drawn. And then we draw FI. And then we draw ID. Okay, see what is then missing there. Whether the complement of G has a Hamilton path. Okay, we argue that the complement of G can be redrawn in the way at the bottom so that the two graphs are isomorphic graphs of the complement of G. But now you can always look very carefully at the fact that, for instance, the degrees, and the fact that in both cases, here E is of degree 1, and G, for instance, you see that G itself is actually of degree 3, and it's of degree 3. So, right, note and that this is possible. So you can just redraw it like that. Right, so in the end, the most important thing is that each vertex has the same degree. So these two graphs will be isomorphic, and they're adjacent vertices of certain degrees, they're also adjacent in both graphs. So the graphs will be isomorphic and they can be drawn in many ways. So we know, therefore, that a Hamilton path is given by, okay, a Hamilton path is given by what? By EI A, we shall analyze that H, B, F, D, C, G, or it's not a circuit, the path, or the initial and the final points are not and do not coincide. E, I, B, F, G, A, H, D, C, etc. So a Hamilton path is given by, okay, let's look at the first one. Is given by E, I, A, H, B, F, D, C, G. Or E, I, B, F, G, A, H, D, C, etc. Okay, the realization is therefore that, okay, we look at the diagrams. So now, a Hamilton path in any of these, let's look at the bottom one. It's much nicer, this bottom one. Right, so if you look at E, I, okay, you're looking at E, I, then you go to A, H, right. After you go to H, you go to B. After B, you go to F. After F, you go to D. After D, you go to C. After C, you go to G. We argue that because all these vertices, how many vertices are there altogether here? So you can count the vertices. 1, 2, 3. Okay, then you have 3 here, you have 2 there, so it's 3, 6, and then 9. Okay, so you count 2, 4, 6, 8, 9. Right, so obviously it's a Hamilton path because it begins from E and it ends at G, but it has passed through all the vertices, right? Or this one here, etc. So now whether the complement of G has a Hamilton path, so the answer is yes. The complement of G most certainly has a Hamilton path. Okay. Right, so yes, the complement of G is a Hamilton path. Right. I think that this will be the next question. All right, for the graph below, here's this graph. Whether the complement of G is bipartite or not. Is the complement of G bipartite or not? Okay, we drew it on the other side. But it is very important to realize that the complement, right, the complement of G is not bipartite. We'll explain that. It's not bipartite. Right, and we'll discuss why it is not. Because bipartite graphs have even seconds. Okay, there's a theorem I'm going to give at some point, and not just be now. Right, because of time. Right, so the complement of G is bipartite, is not bipartite. Right, it's not bipartite because there are circuits that are odd, of odd length. I'll discuss that. So the complement of G is not bipartite since it contains odd circuits. Okay, there's odd circuits. We shall look at the odd circuits that are there in the complement of G. Let's look at an example of an odd circuit that is there. For example, what example of an odd circuit exists? For example, the 3 circuits. Okay, there's a 3 circuit which is the circuit, so it starts from the same vertex and ends at the same vertex. So there's DFID. Let's look at that one. So if you start at D, right? So you start at D, and then you go to F. And then you go to I, and then you go back to D. Okay, so um, we're looking at the complement, of course. Right, so if you look at, here's the complement, right? So you start from D, right? You go to F. From F, you go to I, right? From I, you go back to D. So obviously, it's very clear here. So obviously, it's taken from the complement of G. Just to remove this because one can think of this graph. So it's taken from the complement of G. It has been drawn on the other side. And so because it is taken from the complement of G, right, so you can take that one or you can take another one, F, B, I, F. Okay, the complement is there. We can't waste time just redrawing the same thing. So because of these 3 circuits, it means, and it's not bipartite because the bipartite one has actually mostly circuits of even length, and therefore the 3 circuits are actually circuits of odd length. And because of that, we conclude therefore that the complement of G is not bipartite. Okay, I'm going to give the theorem in my next discussion on the fact that the bipartite graphs contain circuits of even length. Okay, right. So I think that it's some good time to pause here and we shall continue our discussion next time. We must continue our discussion exactly tomorrow. So must continue our discussion tomorrow. So right. Let me see. And the time for tomorrow. Just 1 second. All right. So I'm really taking the time for tomorrow. Taking the time for tomorrow. All right. Um, okay. Right. Right. Think of 4 p.m. tomorrow. Um, see, yeah. Think of 4 p.m. tomorrow. We can continue with our discussion. Yeah, we still need to discuss a couple of things. Think that we still need to um stretch our discussion. I'm looking at how I can further organize this to enhance our discussion, but also in a way that is enriching and interesting. So we'll discuss that. Right. So let's meet tomorrow at 4 p.m., please. Okay. Right. Let's meet exactly at 4 p.m. So thanks a lot for the discussion. I will send the link to this discussion so that you can follow through. And this discussion means you need to just to take down some notes. I know these things are there. I take these things from material that exists, but it's very important that you take down the notes. Part of the ability to be cultivated is to write and reason, but also familiarize yourself with questions that are in the material, because I must give you the guarantee that the coming exam is not going to come from Jupiter. It's not going to be very strange. It's not going to be like an alien. It's going to be from material that mostly exists. You will have one or two some questions, but yeah, you need to discuss exam type questions that are from basis of questions or question banks. So yeah, I wish that we can discuss that tomorrow, 4 p.m. Thanks a lot for joining us. I'll post the video in the next couple of minutes. Yeah, tomorrow, 4 p.m. Thank you. Goodbye.